Hello, my name is Ezra Huscher, and this is a short overview of a paper just published with Ben Oppenheimer and Alice Lenardi, as well as several other members of the Eagle Consortium, on how the physical properties of the circumgalactic medium change over time. I'll step through some of the highlights here. So we looked at a set of high redshift, high resolution zooms from the hydrodynamic simulations of Eagle and compared them to a similar set of Eagle zooms at low redshift. Now, high redshift here being z of 3 and low redshift being a z of 0. So also, we chose to divide the CGM gas into hot and cool phases at 10 to the 5 Kelvin, as that ended up being the neatest division at both redshifts, as we show here in this plot. So we start with some lovely visuals of the physical properties, density, temperature, metallicity. With our high Z and low Z data sets, we have 9 halos in each. So here we picked an example halo from both. But throughout the paper, we tend to average together the 9 from each group to get broader statistics. So first we look at the mass distribution. What we see is that at high redshift, the halos tend to have a similar amount of hot and cool gas at R200, but at low redshift, the hot gas really takes over and has about 5 times the amount of cool gas. And so also looking at the mass fractions, we see that the high redshift hot gas predominates in the interior. It then gives way to cool gas in the middle and then predominates again further out. At Z of 0, there's more gas until about 0.25 R200, where it switches places entirely with the hot gas, which predominates throughout the rest of the halo. So then looking at the inflows and outflows, we see that at high redshift, the hot gas is strongly outflowing. And the cooler gas shows light inflows until about R200, where it really gets moving at about 150 kilometers per second. Compared to the low redshift halos, we do see a fairly similar trend, only the velocities are smaller. The other major difference is that the hot gas stops outflowing and begins inflowing much closer in at low redshift, where at high redshift, you can see that we don't start seeing inflows until way out, about 2 R200. And so as for the rotational velocity, we can see that cool gas has a strong positive rotation further in, probably suggesting disk-like structures in this vicinity, particularly at low Z. A similar story with the metals. Here. Concerning the angular momentum, it's clear that cool gas shows much more angular momentum than the hot gas at both redshifts. You can see the blue dots in these plots. We also see that at low redshift, the spread of the angular momentum gets much smaller between the gas phases. So if you have interest, in this paper, we also get into the angles of separation between the angular momentum vectors. We examine outflow fractions of gas and metals more closely. And we look at volume-weighted quantities like entropy and pressure. So we're working now on a follow-up paper comparing these same Eagle zooms to observations to see how well they can reproduce metal absorption lines at high and at low redshift. So please do email us if you have questions. All right, cheers.